So we will look at the structural breakdown of Euler-Maruyama discretization and how it translates continuous mathematics into computable reality, specifically its dual application in Deep BSDE architecture. So we begin with the core conflict. In theory, continuous stochastic differential equation, or SDE, exists across an infinite continuum of time, assuming infinite precision and boundless resolution. But computers are finite state machines. They possess limited memory allocation and operate in discrete clock cycles, meaning to compute the continuous reality, we must shatter it into discrete sequential blocks. To do this, we build the scaffolding of computation, the continuous lifespan of our process from 0 to t is forcibly partitioned into m distinct increments. By doing this, time no longer flows, it steps. Of course, we're dealing with the stochastic systems, meaning we also have to discretize randomness. We capture this with the Brownian increments, which act as like a bucket of noise. This accumulated randomness is drawn from normal distribution, meaning the width of our temporal bucket is strictly dictates the variance of the injected noise. Now this brings us to the engine itself. The Euler scheme acts as our localized translation engine. To generate the next discrete state, the update rule takes the current state node, calculates the expected forward momentum, and then injects the localized stochastic diffusion. We can visualize this as a vector of assembly line. We start at the anchor point, we apply a predictable push based on the time step, and then append the stochastic noise, this part, to arrive at our discrete state. So we end up here. But there is a cost to shattering reality into blocks. Discretization inherently destroys information. We measure the absolute pathwise penalty of that destruction using strong convergence. This is a strict metric that calculates the expected distance between the true continuous state and our discrete approximation at the terminal value t. So the Euler Maruyama carries what we call the order of 1/2 tax on computation. This means the error shrinks strictly in proportion to the square root of the step size. It imposes a brutal tax on computational resources. To simply double our accuracy, we are forced to quadruple our grid resolution. But in modern algorithmic finance, evaluating high-dimensional models triggers the curse of dimensionality. So to survive this, our discrete grid must serve two masters simultaneously. The identical Euler discretization grid through the rough Burgomi simulation on one side, and the Deep BSDE optimization on the other side. So on the first track, we have a forward path generation. Moving forward from 0 to t, our goal is to generate realistic high-dimensional asset paths and volatility surface. The mechanism here is Monte Carlo path generation built purely on the sequential Euler state updates. On the second track, we have the backward optimization. Here we move backward in time from t to 0, anchored strictly by a known terminal condition. Our goal is to learn the optimal gradient and solve the high-dimensional PDE, such as pricing with default risk. The core mechanism involves replacing spatial gradients with deeply connected neural network layers that are optimized with stochastic gradient descent. So, when we bring this together, we achieve a mirrored architecture. The core insight is that the identical Euler grid acts as a structural skeleton supporting both the forward physical simulation and the backward algorithmic optimization. We can summarize this dual application in the forward-backward paradigm matrix. Rough Burgomi steps physical state variables forward using the Monte Carlo generation to simulate asset paths, while the deep network solver runs backward, leveraging neural network weights optimization to learn the optimal gradients. Now, if strong convergence guarantees that increasing our grid resolution tightens accuracy, theoretical math suggests we should simply slice time into infinitely thin, pushing m to infinity. But computation is not theoretical. As m scales, our dual-track architecture faces an explosive collision between neural network depth and the hardware processing limitations. So we hit an asymptote of effort beyond a certain threshold. Throwing massive compute at the grid yields mathematically invisible gains in accuracy. Because of the half order or 1 over 2 limit, our approximation error rate plateaus here, while processing time exponentially increases. Therefore, engineering mastery is not found at infinity. It is found at what we call the zone of pragmatism. This is a precise tuning of M, where the marginal reduction in approximation error perfectly balances against the marginal cost of Deep BSDE layer optimization. So, the conclusion, while continuous theory is beautiful, computation is powerful. But by aggressively discretizing stochastic reality, mapping its physical limits, and leveraging a rigid grid for both forward simulation and backward learning, we turn pure mathematics into one operational engine.